Hello, and welcome to the Charge Separation and Storage Unit of Phys 1204. In this lecture, we're going to look in detail at the energy transformations that take place when we separate positive and negative charges from each other. Let's return to one of the very first examples of charge separation that we saw. Suppose we take a plastic rod and rub it with wool, so that they both become charged. As we do so, we are exerting forces on the system of the rod and wool with our hands, and so we're doing work on it. And initially, all that does is produce thermal energy in the system. Although the wool is now positive and the plastic rod is now negative, those positive and negative charges are still right next to each other, and so they don't have any potential energy. But now, as we separate them, we have to pull the rod and the wool apart, and that means we're acting against the attractive electrical forces between them. And so we do more work on the system and increase its electric potential energy. This is an example of what always happens whenever we separate charge by any means. We must do work in order to separate the charge. And that work is always positive work on the system of the things that are being charged. We always have a positive and a negatively charged object, and we are pulling them apart, and they're attracting each other. And so we must exert forces, in this case, on object B, in the direction of its motion, and so we do positive work on it. And that positive work within the system acts to increase the system's electric potential energy. Note that once these are separated, there is now an electric field around them, and that will interact with other objects. But don't confuse the work done on the system of A and B with the potential difference due to A and B. These are different things. We did work on A and B, and so they gained electric potential energy. Now, if we think of some pair of positions, 1 and 2, and a path between them, if we were to take some other charge and move it from 1 to 2, then we could define the potential difference between 1 to 2 as the negative of the electrostatic work done on this probe charge divided by the probe charge. But note, this work is a very different work from the one we did to separate A and B. The potential difference between 1 and 2 has come about because we've separated A and B, because we've done that work, but these are two quite separate things. If all we could do with electricity was separate charge by rubbing things with our hands and pulling them apart, then this wouldn't be very technologically useful. But we can build devices that separate charge. A good example is a Van de Graaff generator. It's not really important that you understand how a Van de Graaff generator works in detail. It's just a very good example of a charge-separating device. In the Van de Graaff generator, there are two pulleys and a non-conducting belt that runs between them. The belt gets charged at the bottom. In simple cases, it just rubs against something as the pulleys make the belt move. And that charges it, and the charge is carried from the bottom pulley up towards the top pulley. That charge can be positive or negative. Whether it's positive or negative largely depends on what the belt is made out of and how it's charged. The diagram is showing a case where it's positive. The charge is then transferred to a metal comb. The reason it transfers is that the charge very near the comb polarizes the comb. Its tips become very charged with opposite charge to what's on the belt, and so they pull the charge off of the belt. Then, because that metal comb is connected to a hollow metal sphere, and we know that charge collects on the outside surface of metals, the charge distributes over the surface of the sphere. Note that once the sphere starts becoming charged, there's an electric field generated by the sphere. And as the Van de Graaff generator now moves charge up the belt, it is doing work carrying that charge against the forces that the E field exerts on the charge on the belt. And so, like any other situation of charge separation, positive work is being done. In class, you've seen a rather small classroom Van de Graaff generator. But don't think that that's all Van de Graaff generators are. The early generation of particle accelerators were often made by just building very large Van de Graaff generators. As you can see in this picture, many of them were quite large. A question that's worth thinking about is where the energy is stored when a system has electric potential energy. Thinking back to springs, it's sort of obvious that when we stretch or compress a spring, then energy is stored in the spring. However, where is energy stored by the action of field forces, like the gravitational force when you throw a ball up in the air, or the electrical forces when we pull two oppositely charged objects apart? One perspective is that it's stored in the configuration of the interacting objects. As we move them in both of these cases, we give more room for the field force to act over to do work on these objects. But an alternate way of viewing it is that the energy is stored in the configuration of the field. Literally, we think of it as being stored in the space containing the field. Since the field is just an abstraction and a way of thinking about the electrical interactions, these two models should be equivalent. It's time to check your understanding. So think again about the plastic rod being rubbed with the wool and the energy transformations. But this time, suppose you are rubbing the plastic rod with the wool, and we include you in the system. Draw the correct energy bar chart now that you are included in the system.